Hello guys, today I'm gonna solve an exam. It's a final exam of electrical engineering, Cairo University, third year of electrical engineering. It's a final exam in power systems academic year. It's an academic subject. It's an academic curriculum syllabus. Today I'm gonna show you how to solve this exam in this video. So let's begin with the first question. In the first question, it tells, explain briefly 5 of the main factors to be considered in the transmission line conductor. So, first factor to be considered. So let's say this is A, this is A. The first factor to be considered in designing a transmission line parameter is actually number 1, the amount of power. The amount of power um, the amount of power, active power I mean, it has to transmit. That's the first design criteria. Secondly is the current carrying capability. The current carrying capability of a transmission line conductor. That's the second one. Next up is the third design criteria to be considered in the design process of the transmission line. Let's go up to the next one, which is the third design criteria, design factor. The third one is the permissible voltage drop. The permissible voltage drop. There's quite so many transmission line criteria or design criteria of transmission line. So the permissible voltage drop, that's the third one, voltage drop. Next up, the fourth one is actually the distance over which power has to be carried. Over which power has to be carried. That's the fourth one. The required is to mention 5 at least, so there is the remaining one design criteria. So the remaining one, let's say short circuit level. Yeah, short circuit level. There's quite so many other design criteria to consider. So the fifth one, let's say short circuit level. Sixth one, let's say ease of installation. And right of way. And there's quite so many other factors to consider in the design process of a transmission line. Right of way. let's say another one, which is the urban congestion to be considered. Urban congestion, that is one of the main factors that influence the possibility of designing a transmission line. So in congested areas, it's less likely that a transmission line is going to be installed there, or a power transmission tower can be installed over there in areas where there's a lot of population, there's a lot of people over there. Let's go to the eighth point, which is I said urban congestion, and the other one was environmental considerations. I'll try to remember as best as I can. Environmental considerations. Environmental considerations. Excuse me for the handwriting. It's a bit messy. The ninth one, environmental considerations, urban congestions, load growth. No. Population. Load forecasting and population growth. Was it like that? Forecasting and population growth. That's good. That's enough now. There's two other factors to be considered, but that's quite enough now. I'll not try to remember all of them. That's enough. Cool. Let's go to the next question, which is compare between HVDC, HVAC in terms of power losses, voltage control, insulation needed, asynchronous connections, and cost. What are the disadvantages of HVDC? Okay, so first, we've got to compare between the two in a number of terms, a number of points of comparison. So there's the two systems, the HVAC, high voltage direct current system, and the high voltage alternating current system. So let's have this table over here, table of comparison between the two. Here's HVDC, HVAC, VDC, HVAC. Let's list another column for the points of comparison. POC. Okay, so let's write it with the blue. In terms of power losses, so here is power losses. The HVDC is less power losses. And HVAC more power losses compared to HVDC. Power losses compared to HVDC. Next up is the other. Let's go to the next point of comparison, which is voltage control. Voltage control. So here it is. Here in HVDC, better voltage regulation, and better controllability. Let's write them down as a text. I'm quite tired from that. Controllability. That is controllability. Let's write it as a text. I'm really tired from that. So here, let's increase the font size. Let's make it around 26 or something with the same font type. Yeah, let's make it 26. So that's less voltage regulation. Less voltage regulation. And less controllability. Good, that's the HVAC. HVAC has less voltage regulation in comparison with HVDC. Let's go ahead to the next up. Next point of comparison, which is voltage control insulation. So here, insulation. Less insulation here. Less insulation is needed. And here, more insulation. Insulation is needed in comparison to the HVDC. Is needed in comparison with HVDC. Let's write it down here or there. Doesn't matter. With HVDC. Okay. Next point of comparison is voltage control, insulation needed, asynchronous connections, and then the cost. Okay. So let's extend the line more. Let's extend it more. I like it to be perfectly vertical. I'm quite obsessive about it. Let's extend this line again. Let's make it perfectly vertical again. Perfect. Okay. Let's go to the next point. Asynchronous connections. Okay. Let's write it down here. Asynchronous connection. Imagine asynchronous connections. So asynchronous connection over here. Here is possible. In HVDC, it's possible to link two different frequencies. Asynchronous, which means two different frequencies. Possible asynchronous connection. Asynchronous connection. And here in the HVDC, not possible. Asynchronous connection ain't possible. Asynchronous connection is not possible. Okay, that's great. Next up, what was it? The coast? Yeah, coast of the line. Okay. So, the coast. More cost. Coast of the line. Or the coast itself, let's say the coast. Here, this is less coast. beyond the break-even distance. The break-even distance. Let's make sure of it. Let's continue. We have previously said, let's just recently saying that the cost of the HVDC transmission line costs less than the HVAC beyond the break-even distance. Let's add this. So let's coast beyond the break-even distance, and here more costs more. So here line cost is high. Line cost is high. Let's coast beyond the break-even distance due to fewer conductors. Due to fewer conductors. Okay. Great. That's the cost. Is there any other factor to compare them? Oh, it's over. The points of comparison are over right now. So let's take a look from a broader vision. So here is the points of comparison. HVDC, power losses, that's less power losses, that's more power losses to HVDC. Voltage control, better voltage regulation, and better controllability. HVAC, less voltage regulation, less voltage controllability. But wait a minute, I just forgot something to mention. The reason why more power losses compared to HVAC are on the HVAC due to that was due to skin effect, and corona discharge. Actually, that's the most silly part, asking you about informations, not problems, not mathematical problems, not mathematical formulas. So it tests your ability to memorize so many stuff, theoretical stuff, you know. So that's the other points of comparison, right? And next point is mention the disadvantages. Zoom. Disadvantages of HVDC system. Disadvantages of HVDC system. Okay, what are the disadvantages? Number one, injection of undesirable harmonics. Undesirable harmonics. Harmonics due to power electronic devices. Power electronic devices. Okay, like converters, rectifiers, filters, and so on and so forth. Filters and so on. Power electronic devices used to rectify the AC from the terminal stations. Let's write it down with red. From the terminal stations. Good. Great. Let's go ahead to the next one. Next disadvantage, which is after undesirable harmonics, we say the terminal cost, high terminal cost due to the usage of power electronic devices as well, the same as the previous one. Electronic devices, electronic devices, devices such as converters, rectifiers, inverters, filters, and so on and so forth as well. Third one is what is third one? Yeah, complicated in design. HVDC towers, complicated. So HVDC. Let's make sure. Let's continue. HVDC link is still somehow complicated in design. Complicated in design. Okay, fourth one, which is very important, lack of reactive power. Lack of reactive power. Lack of reactive power, although power factor is improved with HVDC. So there's lack of reactive power. Okay, that was the disadvantages of HVDC systems. Let's move on to the next one. The next one is what's meant by transposition of transmission line, when is it used, or its advantages and disadvantages. Okay, so what's meant by transposition? Definition of transposition of transmission lines. So let's find another more space, wide space. Okay, transposition of transmission lines. Okay, what is transposition of transmission lines? Well, it's a process of exchanging positions between the three phases, over an equal interval interval during one cycle such that each conductor occupies the position of every other conductor over an equal interval. And the process is something like this. It's like you have the three phases A, B, C, D. A, B, C. Okay. Here are the three phases here. A, B, and C. We've got another three phases. Let's just put them like that. Let's put them like this. I'm quite obsessed about making it perfectly horizontal. Okay, so here it is. And you've got to cut it through that. And the exchanging of position here is applied if A takes the position of B, and B takes the position of C, and C should take then the position of A, and then after C has taken the position of A, it should take the other interval the position of B, and if B has taken the position of C, then in the other interval it should take the position of A, and if A has taken the position of B, in the next interval it should take the position of C, and here it is. So that's 1/3 of a cycle. So let's divide this as very fine line. Okay, so let's say no. We say that this interval is 1/3 cycle, 1/3 of a cycle, and that one as well. Next one is 1/3 of a cycle. That one is 1/3 of a cycle until each phase returns to its original position, which was A, B, C, and that happens in unsymmetrical spacing. It occurs. This process occurs among un, among un, unsymmetrically spaced conductors. Great. So you put it like that, and you put the 3 points here. Here a point. Here another one. Let's say here. That's B. That is C. Say here. So we see that it's obvious that they're not forming an equilateral triangle. So that's what we call unequilateral spacing or unsymmetrical spacing. Unequilateral spacing. So this is unequilateral spacing. Equilateral spacing. Great. So that's 1/3. I'm sorry, I forgot to say here 1/3 of a cycle. And after some time, it returns back to its original position. That is what's meant by transposition. What are the benefits or main advantages? Advantages. What are the advantages? Excuse me, my handwriting is not the best thing. Okay, let's write it as a text. Advantages: equalizes uh, balancing the inductance, the overall inductance per phase over one cycle, or one complete cycle. The overall average inductance, per phase over a complete cycle. That's number one. Number two, let's say it equalizes capacitance to neutral per each phase over one complete cycle as well, over one complete cycle causing a balanced circuit. So let's add something here, causing a balanced circuit. Okay, let's say the disadvantages. That's the best that I can remember right now about the advantages. Let's move on to the disadvantages. What are the disadvantages? Stations. Here's so frequent exchanging. Yes, frequent exchange of positions. Positions weakens the supportive structure of the conductor, which increases the cost of installation. Let's check it. Let's move on to the next one. Next question. The transposition. What is PTC? What does it stand for? Power transfer capability. Mention at least 3 methods that can be used to increase it. That question is so silly. Let's answer it. What does PTC stand for? What does PTC? So PTC. What does PTC mean? It means power transfer capability. the ability to transfer power. Power transfer capability. Three methods. Capability. Here's why. Okay, capability. Power transfer capability. Good. Let's move. Three methods to increase. Methods to increase it. To increase PTC. The three methods are: number one, PTC equals V sending times V receiving divided by X line times sine the delta. So consider delta equals 90. What the fuck is that? Consider delta is 90. So if you have transmission line and you're just expressing it, representation of a transmission line as just inductance, you neglect the resistance of the transmission line. Though this is not so acceptable, but let's assume we neglected the resistance of the transmission line, and here is the generation station, the synchronous generator here. Here's XL. This is the load. Okay, so what's the problem? That's V receiving with an angle 0. That's V sending with an angle of delta. Let's continue. So first method is by increasing the sending end voltage. The receiving end voltage. The receiving end voltage. So if PTC1 equals Vs VR1 divided by XL, sine delta is 1, PTC2 equals Vs VR2 divided by XL, so PTC2 divided by PTC1 equals VR2 divided by VR1, so this is increasing. Increment of the power transfer capability by increasing V. So since VR2 greater than VR1, the receiving end voltage, so PTC2 is greater than PTC1. Okay. Next up is using a parallel circuit, double parallel circuit. So XL here, we're just manipulating the value of the inductance of the transmission line. So XL2 equals XL1 divided by 2. So since the denominator is a numerator, so PTC2 equals twice PTC1. Therefore here, since PTC2 equals VSVR divided by XL1 divided by 2, so it's going to be the double, twice as much. So the third one is by using bundled conductors, or bundling, that increases GMR. Therefore, increase inductance. Therefore, increase inductive reactance. Inductive reactance. Of the line. Therefore, increase GMR, decrease. Oh, oops, excuse me. I just guess I'm gonna crop this. Instead of increase, I'll say decrease. Decrease the transmission line inductance, decrease the inductive reactance of the line, hence increase PTC. PTC. Next method, there is a fourth method to mention, which was, what was it? By using series capacitor. Series capacitor compensation. Capacitor compensation. Okay, that's enough. Here is the XL. Here is XC. Negative JXC. And here's JXL. So X total equals JXL minus XC. So decreasing the transmission line inductive reactance therefore increasing the PTC. That's enough. That's great. That's V sending with an angle delta, that is V receiving at angle 0. So they are left unchanged. That's the V receiving over here, and that's the V sending. Here is synchronous generator. Good. That's the fourth one. Let's move on to the next question. What does the acronym FACTS stand for? So FACTS, what's the meaning of FACTS in AC transmission lines, or in power transmission lines, or in power system subject? It means flexible, alternating current, transmission system. Okay, alternating current transmission system. Alternating current transmission system. Okay. What are the mention the merits and demerits of this technology? Okay, merits. First, let's say merits. What are the merits? Let's remember. Number one, what is the merit? Firmer control. First one, firmer control over power flow. That's a very quite important advantage. Number two, um, greater ability to transfer power between controlled areas. Okay, let's move. 3. Always 3. Transfer power between controlled areas. And what was it? Yeah, the third one was secure. So optimized and secure loading of transmission line. Fourth one is improved stability and reliability of the transmission system. Where has it gone? Transmission system. Disadvantages or the demerits. The demerits are injected harmonics, because there is power electronic devices in this application. Injected harmonics. This technology introduces power electronic devices into the transmission line system. Injected harmonics, high initial cost, and cost and complicated analytical modeling. Okay, analytical modeling. Okay, let's move on. Merits and demerits of this technology. Okay, let's move on to the next question, which is a 3-phase double circuit, 50 Hz, transmission line shown in the figure below, and ACSR, conductor whose radius is 0.06 feet. So the conductor radius is 0.06 feet. AB, BC, CB dash, C dash, B dash, they are 10 feet. AB and BC and C dash, B dash, C dash, B dash is 10 feet. B dash, A dash is 10 feet as well. So obtain the following circuit parameters of the line: inductive reactance and ohm. How to find the inductive reactance? First, we have to calculate all the GMRs. So in order to make it more simple, let's copy paste this shape here. Copy this one somewhere over here. Put it like that. So the GMR, let's first find the GMR for capacitance and GMR for inductance. So the GMR for capacitance is equal to GMR AB, GMR AB, that's a cubic root, GMR BC, and GMR CA. Let's find them out. So from the symmetry, GMR AB is the same as GMR CB, isn't it? So GMR AB is the same as GMR BC from the symmetry. Equals how much? The fourth root. Let's do it on AB. So AB dash, the length, geometrical length AB dash times AB times A dash B dash times A dash B, A dash B. So it's fourth root AB dash. What is AB dash? It's 16 plus 10. 16 plus 10 under the root, so we've got 16 square plus 10 square. What is AB? It's 10. What is A dash B dash? It's 10 as well. So here's 10, here's 10, here's the same square root A dash B, the same as AB dash, so it's 16 square plus 10 square. That's a fourth root, and let's find this. If you found it with the calculator, it's going to be 13.73607 feet or meter feet. It's given on feet. Is this GMD or GMR? I apologize for writing it wrong. It's GMD. Let's correct this. Excuse me. This is not GMR. This is the geometric mean distance, GMD. But this is GMD for AB. Let's find out GMD for CA equals the fourth root of what? CA 16 times 20 times 16 times 20. So it's 16 times 20 squared. Let's delete this. How much do we get? Same fourth root, but 16 times 20 squared. Square 16 times 20. That is 17.8885. Enough approximation. Next up, calculate the GMD. We already have written rules, so it's going to be the cubic root of this number, 13.73607 times itself, 13.73607 times 17.8885. How much is that? Square root 17 point, what's cubic root? 17.85 times 13.73607 squared, which is that. So it's 15, approximately it's 15, it's very close to 15.0003, that's very close, feet. That's the GMD. Okay, so the GMD is now calculated very well. Let's move to the GMR. So you've got to calculate the GMR for the capacitance and for A dash. You got to calculate as well the GMR A dash CC dash is form symmetry equals to GMR, the capacitance CC dash equals how much, and you've got to calculate the GMRC as well of BB dash. So the GMR is the square root of the R times the D, and the R was 0.06 feet, was 0.06 times the distance, which is square root of 16 plus 10, square root of 16 square plus 10 square. So what is this equal to? It's going to be equal square root 0.06 times square root 16 square plus 10 square is going to be 1.06399 feet. Nice. GMR BB dash is square root of 0.06 times. It's not the square root times, just directly the distance is 16, so it's times 60. Much is that? If you calculate it, it's going to be equal to 0.979796. 79796. Okay, feet. Let's continue. So that's the GMR, but for capacitance, what about the GMR for the inductance part? Let's put some line, separate between them. So GMR for the inductance A dash, the same calculation applies, but with a slight difference. GM, not C, GML, CC dash equals point, same thing, .06 times e to the power of negative 0.25 times the same square root of 16 squared plus 10 squared. Okay, how much is that? It's going to be equal to 0.93897. GMR L for BB dash is equal to square root 0.06 times 16 times e to the power net 0.25. Let's put the exponential over here, put this over here, put this over here. Okay, and find out what it's equal to. Point 0.25 is 0.86467 feet. Let's try to find it out. Let's try to find it out. So what's the required was to find the inductance. So inductance is omega times L. It was 2 times 22 divided by 7, 2 times pi, times the frequency was 60 Hertz, times the inductance, which is 2 times 10 to the negative 7. That's a three-phase inductance, Len what? Len the GMD divided by the GMR. So what was the GMD? 17, what was it? 15. So it's approximately 15 divided by the GMR of inductance. The total, I forgot the total. Okay, so the GMR total C equals cubic root of 1.06399 squared times 0.979796, and this, and the GMR here as well will be of the inductance will be 3.93897 squared times 0.86467 equals how much? That is equal to how much? Cubic root 1.06399 squared times 0.979796 all squared. What is this equal to? 1.03515 feet. Cubic root of 93897 squared times 0.86467. How much is that? 0.91351, say 252 feet. Okay. GMRL 0.91. 0.91352. How much is that? Okay, so I just made a mistake here. It's a very fatal mistake and silly at the same time. So that was not 10, it was 20 feet. 20 feet, that was as well 20 feet. That was 2020. So let's recalculate these values and delete that. Delete this. Delete this. And delete this. let's move. So if you calculate this again, 0.06 times the square root 16 squared plus 20 squared is going to be 1.23. 1.23966. What is this? 1.23966. That's the square. Let's find it in another version for the geometric mean radius of the inductance. So it was 1.09399, 1.09 feet, 9399, and here's the square. Let's calculate them. Square root 3, 1.23966 squared times 0.979796, which is that 1.1462. Great. What is that? Other one is square root 3, 0.09399 squared times 0.86467, which is that 1.01148 feet. So here GMRL is 1.0. 1.01148. So the required of the question. So the required of the question is to find the inductive reactance per mile per phase. So it was the frequency was 50 Hertz. Let's return back to the question. Single phase 50 Hertz, double circuit 50 Hertz transmission line. Shown in the figure below is an ACSR aluminum conductor steel reinforced conductor whose radius is 0.06 feet. If AB equals BC equals C dash B dash 10 feet, that's 10 feet. That distance is 10 feet, and that distance is 10 feet, and that distance is 10 feet as well. The spacing between the conductors is all 10 feet vertically, but the horizontal is 16 feet. Okay. And the radius is 0.06. This is the radius of the conductor. This radius of the conductor is 0.06 feet. The inductive reactance in ohms per mile per phase. Ohms per mile per phase. Per mile, which means the inductance that we are calculating actually is per meter. So the one mile is having 1,609. Let's write it down over there. Let's go here. Yes. Times the length. But before the length, let's multiply. So if you get it like that, you get the answer in Henry per meter. So the 1 mile equals 1,609 meter. So if you say a 1 meter is 1 divided by 1,609 of the mile, is a fraction of a mile. 1 meter is a fraction of a mile. So 1 divided by 1 meter, 1 meter is actually equals to 1,609 divided by a mile. That might sound pretty weird, but if you flip this equation upside down, you get that 1,609 gets up and mile gets down and 1 meter gets down. So I flip the equation upside down. So Henry divided by meter equals 1,609 times Henry divided by mile. So if you want to get it on Henry divided by mile, you have to multiply by 1609. So we can just make it easier on ourselves and calculate it in one shot. So here is the multiplication, 1609, to get it in ohm per mile per phase and get it in one shot. Alright, so I've got 2 times 22 divided by 7 times 50 times 1609 times 2 times 10 power negative 7 ln 15 divided by 1.01148. This thing is equal to 0.7.27273 ohm per mile. Okay, that was, I'm sorry, excuse me, that was ohm instead of Henry, but it's not so much difference actually. So that's the final answer for the inductive impedance, inductive reactance. That was part A of the question. Let's move on to part B. Suggest a more simple, faster method to obtain the above value. Compare between the values obtained. Which method offers more accurate results? Okay. Suggest a more simple and faster method to obtain the above value. Compare between the values obtained. Which method offers more accurate results? So a faster and more simple method. Let's move on. We're here, faster method. The faster method is, we say that the GMD equals the cubic root of those distances. This distance is 10 feet times this distance, it's 10 feet, distance between A and B, the spacing between the phases from A to B and from B to C and from A to C, that is 20 meters, 20 feet, that is 10 feet, and that is 10 feet. So we got 20 times 10 times 10. So if you found that 20 times, it's going to get 12.599 feet. Okay, that's the GMD. So inductive reactance is equal omega times L equals 2 times pi times the frequency 50 times, if you want to get it exactly, want to get it again in ohm per mile, you get to multiply by 1609 times 2 times 10 or negative 7. The ln of the GMD divided by the GMR, it's 12.599. It's a very simple method. Divided by how? Divided by 0.06 just alone? No. Divided by 0.026 times exponential power negative 25. Let's get it in a bigger handwriting. Let's get it bigger. It's here 12.592, and down here is 0.06, the radius, but multiplied by the exponential of negative 0.25, negative 25 here. So how much is this equal to? The inductive reactance is going to be equal to 2 times 22 divided by 7 times 50 times 1609 times 2 times 10 power negative 7 ln 12.5992 divided by 106 exponential negative 0.25. And since this is a double circuit, so XL total is going to be XL divided by 2, so it's going to be equal to 0.566069 divided by 2. If I divide this by 2, gives 0.28303 ohms per mile per phase. And in comparison with the other value, what was the other value? The other value was that. Comparison between the two values. Found out we find out that they're very close, 2727 and 283. Very close, but the more accurate, which one is more accurate is the other question. So the more accurate method is the more accurate method is the first one. Okay, let's go ahead to the next one. The next question. So what was this? That was part B. Let's go to the next one. Part C, capacitive susceptance in Siemens per mile per phase to neutral. That's pretty easy. Capacitive susceptance omega C. So where am I here? So capacitive susceptance C, straight line. Capacitive susceptance, so it's a symbol expressed as BC equals omega times the C to neutral. It's B to neutral. So C to neutral, how to calculate it? 2 times 22 divided by 7 times 50 times 1/6 per mile per phase. So we multiply by the same factor again to convert between mile and meter. How many parameters is 1609 per miles? Times 2 times 22 divided by 7 times the constant epsilon naught, the relative permeativity, electrical permeativity, 812. Remember, and this is ln the GMD divided by the GMR. What was the GMD? It was 15, approximately 15 divided by the GMRC was something else. What was the GMRC? 1.1462. Very good. So it's here 1.1462, and it's not very formidable task to do. It's 44 divided by, say, 44 divided by 7 square times 50 times 1609. So 8.85 times 10 power negative 12 divided by the ln 15 divided by 1.1462. How much is that? So here is what 1 point it's actually 1.09389 times 10 power negative 5 Siemens per mile. Siemens per mile. That was Siemens per mile per phase. Okay. Let's move on to the next question. So that is, second question is over. It's finished. Let's move on to the third one, which is not very difficult question. Figure 2 shows 230 kilovolt, 3-phase, 50 Hz transmission line connecting two areas. The line has an inductive reactance X of 60 ohms per phase, and the thermal limit of the conductor is 1.5 kiloampere. The line is equipped with a TCSC, whose XC is 20 and XA is 5 ohms. What does TCSC stand for? So TCSC is thyristor, is defined as thyristor controlled series capacitor. Series capacitor. Okay, B. Next question. Mention the merits and demerits of using TCSC. Merits. That's another question repeating itself. That was the same question as in the first question. Mention the merits and demerits of facts. So facts is TCSC is a special condition of facts, or a special technology that lies under the classification of facts. So merits are number 1, firmer control over power flow. Control over power flow. The second one is greater ability to transfer power between controlled areas. 3, secure, optimized, and secure loading of transmission lines. Transmission lines. 4, and the last merit is improved reliability and stability of the system, of the power system, or the transmission system. The demerits are demerits. Initial high, initial cost, initial cost, high initial cost, and injection of harmonics. Of harmonics complicated and complicated analytical modeling. Okay. Maximum three-phase nominal power the transmission line can carry. So the P nominal equals square root 3 times E times I. What is E here? It's 230. So here it is 230 kilovolts, 30 kilovolts times 1500 or 200? 500, okay. 1.5 kilo amperes. So it's 1.5 kilo amperes. And don't forget root 3 as calculated as estimated as 230 times 1.5 root 3. How much is that? It's 597.558 megawatts. That's the nominal power, D. Create the maximum, compute the effective impedance of the line when all the thyristors are switched on. You see, as all the thyristors are switched on, that's the short, that's the X effective, that's 60 ohms, 60 ohm inductance, and that is 3 parallel branches. So X effective equals JX plus 3 times X parallel, and X parallel equals JXA. What was XA? J5 minus J20, J5 times minus J20 divided by J5 minus J20. How much is that? -5i negative 20i, 5i minus 20i. That is 6.667 J. Right, very good. So X effective equals J 60 plus 3 times J 6.67 equals J 80 ohm. Okay, let's move to the next one. Okay, next one is obtain the power angle denoted by delta. Q1 thyristors of the TCSC are switched on. Q2, Q3 are switched off. So Q2 is switched off, Q3 is switched off. So you're having now XC and another XC. You're having XC parallel with this branch, XA, because this is turned on. So you find the X effective, the total line. Its maximum nominal power already calculated from the first step. Descending end voltage is 230 kilovolts. Receiving end voltage is 220 kilovolts. So you want to obtain the power angle. So that's a pretty easy task, but just calculate the X effective. So X effective is going to be equal to the X JX plus JX parallel, or X parallel, let's say X parallel plus 2XC, or 2JXC. So it's J60 plus 6.667J. That was XP already calculated on the previous step. 6.667J plus 2 times negative J20. It's negative J20. Very, very good. Okay. So you get STI 6.667I minus 40I. So it's going to be 26.667J. That is X effective. Very good. Let's go ahead and calculate the sine delta. So you've got the P nominal. P nominal equals V sending times V receiving divided by this, the X effective, times sine the delta. So delta equals sine inverse sine of P nominal times X effective divided by V sending times V receiving. Okay, so delta equals sine inverse of P nominal. What was P nominal? It was 59. From first step, it was 597.588, 598 times the effective impedance as an absolute value, 26.667 divided by Vs times Vr, 230 times 220 line values. So delta is how much? Sine inverse 597.559 times 26.667 divided by 230 times 220. Which is that? 120 times this divided by pi. How much? 18.356 degrees. I'm gonna check it out from an answer, from a guide answer from one of my colleagues. Okay, he got it 18.355. That's pretty close to my answer. Okay, so here is the third question. Let's move to the next question. Let's move on to the fourth question. So we have 500 kilometer, 500 kilovolts, 60 hertz, uncompensated. Three-phase line has the following exact parameters. So got the parameters as A.8794 with an angle of 0.66. And you've got B as equal to B equals to 134.8 and the angle is 85.3, and C is equal to 1.688 times 10 power negative 3 with an angle of 90.2. So it's here, the angle is 90.2. At full load, the line delivers 1000 megawatt at 470 kilovolts power factor. So what is this? The receiving end voltage. So the receiving as a phasor equals 475,000 with an angle of 0. That's the reference. Unity power factor. So the I receiving, can you calculate the I receiving is the power divided by root 3 times the V. And I forgot to just divide this by root 3. So divide this number by square root of 3, put it over here, root 3 times the V, the receiving times power factor. Okay, so here is the power is 1000 mega times 10 power 6 divided by, and the angle I forgot to write down, leave up some space for the angle. Here is cosine inverse. The inverse cosine of the power factor. Inverse or negative inverse? Negative inverse, because no, it was no negative inverse because it's unity power factor. So if the power factor here is 1, this is 1. So this angle should be 0. This angle should be 0. So square root of 3 times the receiving end voltage, which was as a line value 475,000. So get that VIR as a phasor is equal to a real number. I need to write down the angle because it's already 0. 6 divided by square root 3 times 475,000 is 1215.474 amp. Let's say, okay, so here it is. That's the answer. Very good. Descending end voltage. Once you get those two steps, it's pretty easy. Next things are pretty easy. A, so descending end voltage, descending equals A times IR, no times VR. Those get confused. VR plus B times IR. What was A is already given. VR is given. VR, you just substitute all of them. So IR is substituted with this value, and VR is substituted with that value, and both angle of 0. So it's pretty easy right now. You save the constant on your calculator, and you just get the answer 47500 divided by root 3 plus B times F shift to 3. How much is that? So it is 300,000 and 303,956.84 with an angle of 33.118. So that's the sending end voltage, B. sending end current is going to be I sending equals CVR plus DIR. You substitute with the C and D. That is C, and that is D. If you want to pause the video to write them down and calculate and check after me, that would be better for you. And VR is here. If you want to pause the video, this value of VR. If you want to pause the video on this value IR. So if you get them on the calculator, left with the following: sending end currents be 1168.22993 with an angle of 24, approximately 24.036 degrees. Okay, the sending end power factor. Sending end power factor. What is the sending end power factor? The sending end power factor will be how to find the sending end power factor. How to find the sending end power factor. It's pretty easy, actually. It's cosine the theta v sending minus theta I sending, so it's equal to cosine 33.118 minus 24.0036. How much is the power factor of the sending? It's cosine 33.118 minus 24.036. How much is that? It's going to be 0.987, and don't forget lagging, because the current is lagging the voltage already. Good. Move on to the next one. The full load line losses. So P losses equals P sending minus P receiving. Of course, the sending end power is more than the receiving end power, so it's square root 3 times 500,000. So it's 500,000 times the sending end current. No, I should delete that. 303,956. 303,956.84 times sending end current, which is 1168.22993 times the power factor. So it's squared 3 times V times I. That's the I, that's the V sending, and that's the I sending. And the power factor cosine the angle, which is going to be this number, which is going to be that, to be the cosine of 33.118 minus 24.0036 minus the P at the receiving end, which is already given at 1000. 1000 power 6 times 10 power 6. We find out the power. So it's square root 3 times 303.956.84 times 168.229 3 cosine 0.118 minus 24.0036. All this shit minus 10 power negative power 9. It's 1 megawatt. What's the problem? Minus the receiving end. What would be the answer? Oops, I should have multiplied by 3 instead of root 3. So let's delete this. Let's delete this one. Should have been 3, not root 3. So that's a phase value, that's another phase value. We always calculate phase values. So right now it's 518. So it's 51.824 or 5284.30656 kilowatts. Or 51 megawatts. 51.824 megawatts. So here that is the losses. E is the voltage regulation. So the voltage regulation is VR no load minus VR full load divided by VR full load. What was the VR full load? VR no load is Vs divided by A. What is Vs divided by A? 3956. So it's 303956.84 divided by A. What is it? 0.897 0.8794 0.8794. But remember that this is phase value, so you got to multiply by 3 root 3 minus the other line value of the receiving end full load, which was 475.30 divided by 475.30. What is the next one? 303956.84 root 3 divided by 0.8794 minus 47500 divided by 47500. Gonna be 26%. 26% voltage regulation. There's no more space for F. Last required. It's going to be recalculate the voltage regulation when identical shunt reactors are installed both ends during light loading, providing 65% total shunt compensation. Calculate the impedance. So first, let's say we have a pi model of the transmission line. that this is y dash over 2, and that is z dash. And that is y dash divided by 2, that is the ground, that's the B receiving. So compensation, mean. What is A? A was in the pi model, it was, as I remember, it was y times 1 plus zy divided by 4. Remember it was. So how to find here? So here's z dash y dash and b equals z dash. From here, how to find z dash or y dash? So from those two equations, y dash, oops, I actually made a mistake here. This didn't exist here. Y dash over here, there wasn't 4 over here. It was 2. So y dash is 2a, a minus 1 divided by b. How much is this? Find it out. A is already given, B is given, all the constants of the transmission line model are given. So y dash is equal to 3.1025 times 10 power negative 6 plus j 1.796 times 10 power negative 3. That's y in Siemens. Okay, that's Siemens. Very good. So y dash compensated equals, after the compensation and installation of a series capacitor. So here in the question, here recalculate the percentage voltage regulation with identical shunt reactors. So it's not series capacitor, it's identical shunt reactors installed at both ends of the line during light loading, providing 65% total shunt compensation. The reactors are removed at full load. Calculate the impedance of each shunt reactor. Comment on the results obtained. Okay. So the y dash compensated is actually equal to 3.1025, same thing, times 10 power negative 6 plus j times 1 minus 0.65 times this number, the same number that like that. This one, 1.79. Also, we copy paste this number, 1.796. So here 1.796 times 10 power negative 3. Okay. So the A dash, the new constant A compensated after compensation is how much? So if you get this number, minus j times 0.796 or negative 3. So A dash compensated is this number times is 1 plus zy z dash y dash divided by 2, and z dash is hopefully equals to b. This is equal to y compensated, so y calc ans, and here is y times b divided by 2 plus 1, shift to 3, that's the new a. It's going to be 0.999 9985 with an angle of 0.012. So there was a mistake here in the value of A compensated. So after compensation is going to be 9578. The angle is 0.2203. The A compensated, so M23 calc plus same thing. Okay, compensated, so the sending end voltage, B sending is how much? Is A dr plus B IR. B is unchanged. This is unchanged. And that is A after compensation, the shunt reactor compensation. And how much is this value? B is given, IR is given, VR is given. We just substitute these, plug in those numbers. So here's M times VR, which was 47500 divided by 3, plus B times F3. So here's 31275, 321. So here's that 321 75.18. The angle is 30.758. So the voltage regulation is going to be 321,275.18 times root 3 divided by 0.9578 minus 47500 divided by 47500. How much is that? So this number E 75000. How much is that? It's going to be 22.316%. So the improvement, the voltage regulation, the comment, the VR has been improved. By where was it? So 26 minus 22.316 divided by 22.3, 26. 15% of its previous value, improved by 14% of its previous value. Thank you guys for watching, and for more YouTube videos, if you want more, let me know in the comment section below. Thanks.